Hi all, this is video 4, class 4 for math 2621 probability for application class. So today we are going to discuss conditional and independent probability, and we will discuss this conditional probability idea again in chapter 3, but in this class in chapter 1 we will learn it has a basic concept. But we will discuss this one further in more details in chapter 3. Okay, so let's start the class. Okay, so I'm going to define the conditional probability first. So before coming to the real mathematical definition, so let's see why we need the conditional probability. So conditional probability will take place when we have additional information about a random experiment. So if you have additional information, so that's mean before performing the random experiment, if we have some additional information, so then we can use that additional information to calculate probabilities, and this will change both the sample space and probability loss. To see how, consider the following example. Suppose we are tossing a coin 3 times. Find the probability that getting exactly 2 head if the toss is head. Okay, so we want to find the probability of getting exactly 2 heads if the first toss is head. Okay, so let's write down the sample space first. So tossing 3 coins at once, so we did write this one few more times and we write it again. Okay, so these are the all possible outcomes when you are tossing 3 coins at once. So this means first one is head, second coin is head, and third coin is head. First one is head, second one is head, third one is tail, and so on. Now this says, let's define 2 events. Okay, so n omega has 8 outcomes. N omega, number of items in omega is 8. Now let's define 2 events A, which is getting exactly 2 heads. So this is getting exactly 2 heads. And B is first toss is a head. B first toss is head. Okay, so now let's find out the probability of let's write down the items in B. Okay, let's write down the items in B. First toss is head, so we don't worry about the position. We only care about the first toss. So first toss is head, then we will take it into our set. Okay, so first 3 has first toss head, and this one first toss head, and that's all. Okay, so these are the all possible outcomes for first toss is head. Okay, so now the question asks, what is the probability of getting exactly 2 heads if the first toss is a head? So that's mean if this happen, what is the probability of getting 2 heads? Okay, now let's write down probability of getting exactly 2 heads if first toss is head. Okay, so now look at this sample values. Here we have calculated how many possibilities you can get exactly 2 heads when it is first one is head. So this is 2 heads, first one is head, 2 heads when first one is head. So it is 2 out of 4. It is 1/2. Okay. So can you see this the denominator now? It's going to change here. It's not 8 now. So far we did NA over N omega, but in this case the sample space is changed because now we are assuming, okay, B happened. If B happened, what is the probability of getting exactly 2 eggs? Okay, so this can be done in another way. Okay, so we can bring this one into the original sample size as well by doing this trick. Okay, so I'm going to divide numerator and denominator by 8. Okay. Okay, so I will write like this. Okay, so here 2 over 4. Okay, so here I'm going to divide this one by 8 and this one by 8. So the numerator and denominator dividing by same number, it does not going to change anything. So now this part I can write as probability of A intersection B, and the denominator is probability of B. Okay. Okay, and this side, this one, I can denote like this: A given B. So the condition related, the event related with if part is in the second position. Okay, and when you're writing B here, the denominator also B. Okay, so that's the idea of conditional probability. Now we can define it. Okay, so this is the idea of conditional probability. If we have extra information, so then when you're finding the probability, it's going to change the sample space. Okay. Okay. So now let's define the conditional probability in a mathematical way. So in the general conditional probability formula is given follows: if A and B are two events with key P is strictly greater than 0. The reason is here PB is in the denominator. So P of B should be strictly greater than 0. Okay, so that's the condition. Then if that's another assumption or the condition we should satisfy to define the conditional probability concept. Then the probability of A given B. So A given B means the B is already happened. What is the probability of happening A? So that's the meaning of this one. What is the probability of happening A if B is happen? Okay, so this is same as probability of A intersection B over probability of B. And similarly, we can define probability of B given A, which is probability of A intersection B. Okay, so the intersection is same. It's not going to change, but the denominator is here now should be A. Okay, so that's very important part. If the given one is B, then the denominator here should be B. If given one is A, the denominator should be A. And there's a condition here. In this case, probability of B should be strictly greater than 0. Here, probability of A should be strictly greater than 0. Okay, so that's the mathematical definition for the conditional probability. So here, this equation for probability of A given B. Okay, so those are the definitions we need to calculate conditional probabilities. Okay, so if the conditional probability is known, we can do something like this. So we can multiply both sides by PB. PB is something greater than 0. So we can multiply by PB. Okay, so I'm going to multiply this one by PB. So what happened here is this B is cancelled here, and A intersection B with PB is remaining in the left hand side, and A intersection B is in here. So this rule is known as multiplication rule. Okay, so this is another useful rule in probability. So we can write the intersection by PB times probability of A given B. Okay. Okay, so now let's do an example to understand these concepts. Okay, so let's see the first one. Find the probability that a single toss of a balanced die result in a number less than 4 if no other information is given, and if part A, B, it is given that the toss is result in an odd number. Okay, so let's do part A first. So part A, we don't want any conditional part because no other information given. Okay, so this is a single toss. So if you toss once a single die, so that means you will get a number between 1 to 6, because in standard die we have 1 to 6, so you will get a number between 1 to 6. So this is the sample space, and let's do part A. So part A, no other information is given, so the event is a number is less than 4. Okay, so I'm going to define an event called A number less than 4, and I can write down the items in this event, which is numbers less than 4. So that means you should get any of these three numbers, 1, 2, 3. So you can find the probability of A, and this is a balanced die, so that means it is equally likely. So you can have NA over N omega. NA means number of items in A over number of items in omega. So it is 3 over 6. It is 1/2. Okay, so now let's see how we can do the second part. Okay, so second part, okay, I will do here B. Now B says find the probability of the result in a number is less than 4 if it is given that the toss resulted in an odd number. Okay, so let's take B is an odd number. Okay, so we don't want to write all the values in B, but let's see what we have to find here. Okay, so we have to find the probability of A given that, if you know, B is an odd number. So we have to find the probability of A intersection B over B. So this is from the definition. Okay, now let's write down the values in B. Now we can write down the values in B. So the odd numbers. Okay, so odd numbers, if you toss 1 to 6, you will get odd numbers 1, 3, 5. Okay, so the question asks what is the possibility of getting a number less than 4 if you get an odd number. Okay, so now we have to find the intersection of A and B. So A is 1, 2, 3, and B is 1, 3, 5. So the intersection here is A intersection B is going to be 1 and 3. Okay, so these are the common items. Okay, so these are the common items in A and B. So it is 1 and 3. So you can find the probability of A given B, which is 2 over. So we have 2 items in. So I will draw right here. So we have 2 items in intersection. So it is 2 out of number of items in entire sample, which is 6 over probability of B. So B, we have in B, which is 3, and A intersection B is 2. Okay, so here I will write down the equations as well. So this probability should be N A intersection B over N omega. and here should be NB over N omega. So NA intersection B, which is 2 over 6, and here NB, which is 3 over 6. So here you will get 2/3. Okay, here you can simply cancel this 6 and hit this 6, so you will get 2/3. Okay, so that's the required concepts we need to discuss in this level, but we will discuss this one again in more detail in chapter 3. So we discuss conditional probability here because we need to know the idea of independence. Okay, so the idea of independence is very powerful one in a probability. So if two events are A and B said to be independent if the occurrence of one does not affect the probability of other. Okay, so if two events are independent means occurring of another event, it does not matter for the second event. Okay. Okay, so for example, we can say raining today. Okay, so if it is raining today, it will affect to the temperature. So that's mean raining today and today's atmosphere temperature is not going to be two independent events. But raining today and studying today, so that can be two independent events. So because if it is raining or not, we will do whatever we need to do. Actually, if it is raining or not rain, you have to watch the videos per day. So those are not dependent events. So those are independent events. Okay, so those are some quick examples we can think about two independent and dependent events. Okay, so now let's see how we can define independency of two events. Okay, so there are two definitions. Okay, so the first definition, suppose first definition is based on conditional probability. So suppose the probability of B is strictly greater than 0, and if A and B are two independent events, so this means if and only if. So this mathematical word, so this is abbreviation in mathematics. So this is if and only if. Okay, so this if IFF is same as if and only if. So if and only if means this is true for both sides. Okay, so if A and B independent, then this true. If this true, then it should be independent. So this is true for both sides. Okay, so that's why we are using if and only if. Okay, so I can write this one this way as well. So if A and B independent, then PA given B should be equals to PA. Okay, so that means given information is not required. So because A given B same as PA, so that means there's no effect for B. Okay, so we can do this one other way as well. If this happen, if PA given B is same as PA, so then this means A and B independent. So this is the meaning of if and only if. Okay. Okay. So the proof is straightforward. So this is how we can prove this one. I will use a different color to show the proof. Okay, so this is how we can prove. So we know okay, so this part is you don't want to prove, but in the next results we can prove. Okay, so this results we can prove. So I will show you how to prove the second results. Okay, second part. Okay, so so we can write the left hand side P A given B P A. Okay, so now I'm going to write this one using the definition. I can write A intersection B over P B equal P A. Now I'm going to multiply both sides by PB because PB is strictly greater than 0. So if I do the simplification, we can see there's another results for independency, which is intersection equals probability of A times probability of B. Okay, so that's the second result. So if you plug this definition for A given B, you can obtain the second result. Okay, so this is the second result is more common to you show independency. So here again it is if and only if. Okay, so the if and only if means if A and B independent, then this should be happen. Okay, so this should be true. Probability of A intersection B should be equals to probability of A times probability of B. So that means left hand side should be equals to the right hand side. If this happen, if this relationship is hold, if A probability of A intersection B is same as probability of A times probability of B, and this implies, then this means A and B independent. Okay, so A and B are independent. Okay. Okay, so this result is very important than the previous results because we will most of the time we will use the second result. That's easy because it is we only need to find the probability of A intersection B and probability of A and probability of B. But if you want to use the first results, this one, you have to calculate the conditional probability and show that one is same as probability of A. Okay, so you can use either way, but the second results is more common to use. Okay, so we can extend this idea of independency into more than one event. So here we only consider 2 events. Now we are going to extend that one into more than 2 events. Okay, so suppose we have n number of events and we can say it is mutually exclusive if this happens. Okay, so if it is mutually exclusive, then PA1, A2. Okay, so let's take so let's take S equal equal 1 to n. Okay, so it says S is subset of n. So let's take S is equals to this n. Okay, then probability of different color. Then probability of A1 intersection A2 intersection all the way to AN is same as probability of A1 times probability of A2 times dot probability of AN. Okay, so if you have a product of different number of items, we can use this notation. So this is uppercase pi. Okay, so this is uppercase pi. So this is used for denote the product. Okay, so this is used to denote and similarly, so this is the mutually independent. So the mutually means the entire set is independent. But pairwise independent means it is independent only for two pairs. Okay, so if you have a set of events, and if you consider any of two events here, Aij, so then this is pairwise independent for all ij's in this set. Okay, so the mutually independent and pairwise independent is two things. Okay, so if it is it's not necessary if it is pairwise independent and mutually independent are same. Okay, so we will do one example to understand that one. Okay. Okay, so before doing the example related with pairwise independent and mutual independent, so we will do one more example to feel the see what is the importance of the idea of independency. So if the coin is fair, okay, if the coin is fair, the probability of getting head of any toss is 1/2. Okay, so consider this example. So getting head of any toss is 1/2. Okay, so that's true. If the coin is fair, so if you toss it several times, it's still, so getting head is 1/2, getting tail is also 1/2. Okay, so let's ij is denote the event when we are getting tail or head in the jth tossed. Okay, so hj means we are getting head on jth tossed, tj means getting tail on jth tossed. Okay, so if the toss are done in independently, so if you're tossing the coin independently, so that's mean your first toss is does not depend on the second toss, and your second toss is does not depend on first toss and the third toss as well. So if you are doing this independently, you can find the probability of getting head tail as follows. Okay, so this method also you can use to find the probability of getting head tail. Okay, so in this one we can write probability of getting head in first trial, head in second trial, and tail in third trial. Okay, so from this definition. Okay, so j means the jth trial. So if you get head in first trial, we can say it is h1, and you have to do the same. You have to get the same. Say in the same series of trial, you have to get head in the second trial. So that's why we are taking intersection, and in the third event should be the tail. So if these three, if you get the three intersection of these three events, so that's mean it's same as the probability of getting head tail. Now, since we are tossing this one independently, we can break these probabilities because intersection can be written in terms of product of corresponding probabilities if two events or two or more events are independent. So I'm going to break this probability into their marginal probabilities. So now this is probability of getting head in first trial. So that is 1/2. Probability of getting head in second trial is still 1/2 because this is a fair coin. And probability of getting tail on third trial, which is 1/2. So it is altogether 1/8. So if you without write down the entire sample space, we can calculate the probability of getting head tail by using the idea of independency. Okay, so this equation hold because processes are independent. Okay, so without giving this information, if it is not doing independently, we cannot use this equal sign. Okay. Okay, so now suppose we are tossing a unfair coin. Okay, so that means it's not a fair coin. Okay, but has so that means each toss has probability of p of getting head and probability of getting tail is q. Okay, so q is 1 minus p. Now it's like 1/3 and 2/3. Okay, so the getting probability of getting head is not same as probability of getting tail, so that means it is not equally likely event. Okay, so if it is not equally likely event, still we can use the idea of independency. So suppose we are going to calculate again head tail. Now we can write this one using the same definition. H1 intersection H2 intersection tail 3. Now since these are independent, we can break it. Okay, so I will write down here. Since independent process, we can write this one has pH1 pH2 times PT3. Okay, so now the getting head 1 is not 1/2, it is P. So now we can write this one P, this one P, and getting tail is 1 minus P, or it is Q. So we can write this one P square 1 minus Q, 1 minus P, or we can say P square Q. Okay, so these are both answers are okay. So the idea means here, so the point here is, it doesn't matter you are tossing a fair coin or unfair coin, still you can use the idea of independency if you are doing the tosses independently. Okay, so if you are tossing the coin independently, you can calculate the probabilities without write down the entire sample space. But if you are doing it independently, okay. Okay, so let's do one more, few more examples. Okay, so in this example, we say for a research study, the table shows the gender and music preference in a group of people. Okay, so the music preference is rock and classical, and there's a gender, male and female, and there are numbers given. So the question asks, if the random experiment consists of selecting one person from the 45 at randoms are random at the event A. So events A is person prefer rock, and event B person prefer classical. So the question asks, is these two are independent? Okay. So let's see how we can approach this type of question. So first of all, check whether here the 12 males are prefer to rock, and 3 prefer to classical. Females, 24 of them are prefer to rock music, and 6 of them are prefer to classical. And if you get row wise total, you will get total number of men in this study. And if you get this row total, you will get the total number of female in this study. And if you get the column total, you will get the total number of persons who prefer to listen rock music. And total, if you get the total of this column, you will get the classical preference for classical music. Okay, so that's how you can interpret the table first, and then let's see what is the question asked. Okay, so the question asks, event A person prefer rock, and event B, a person prefer classical. So the question asks is these two are independent. Okay, so let's see what is the events in A. Okay, so let's find PA first. Okay, so we don't want to list the items in A, we can just find PA. So PA means person prefer rock. Okay, so it is a total number of persons prefer rock. So that means you have to take n rock. Okay, n who prefer to rock over n number of sample space. So in this case, 36 over 45. So we can use a calculator here. So answer is 4 over 5 or 0.8. So you can use either answer, that's fine. But you should provide me the more simpler form. Okay, so now let's find probability of B. Okay, so let's find probability of B, which is person prefer classical. So it is n classical over n omega, which is 9 over 45. Okay, so use a calculator and simplify this one. That is 1/5. Okay, so the question asks, is these two are independent? Now let's find out the probability of A intersection B. Okay, so definitely there is no intersection because there are no people who like both. Okay, so in this case it is 0 over 45. So that means it is 0. Okay, so now we have to check whether is this hold or not. Okay, so you have to check whether A intersection B is equals to PA times PB. You have to check whether this equation, the left hand side and the right hand side is equal or not. Okay, so to check this one, what I'm going to do is I'm going to calculate PA times PB. So I'm going to calculate PA times PB. So which is 4 over 5 times 1 over 5. This is 4 over 25, which is definitely not equal. So this is not equal to 0. Okay, so because the intersection is 0. So this is not equals to A intersection B. So that's mean we can say A and B are not independent, or you can say A and B are dependent. Okay, so that's how you can write down your answer. Okay, so just showing this one is not enough, so you have to say it is independent or not. So in this case A and B are not independent. Okay, so let's do another example and then we are done with this. Yeah, we have 2 more examples and then we are done with this class, this discussion. Okay. Okay, so consider the random experiment of drawing 2 cards from a regular card deck. What is the probability that both are spade? Okay, so in here you are picking card from a regular deck. So this is another standard example in probability, the regular card of deck. So in the regular card of deck we have 52 cards, 13 spades, 13 clubs, 13 hearts, and 13 diamonds. Okay, so those are the main 3 shapes we have, card shapes we have in the regular decks of card. Okay, now here the question asks, what is the probability that both are spade? Okay, so we assume we are taking without replacement. Okay, without replacement. So the without replacement means once you get a card, you are not going to put that one back into the 52 again and to take the next one. So we are picking card without putting the card what we have picked. Okay, so let's write down the sample space omega. So we have 13 spades. Okay, so we have 13 spades, and other cards we have 39. Okay, so not spades we have 39 and spades we have 13. Okay, so now let's define 2 events. So let A is the first card is a spade. The first card is spade, and B is the second card is spade. Okay, now let's find out probability. So PA, first card is spade, which is first card is spade. So we have how many items in the, so I'm going to write down the entire one. Total number of spade divided by total number of sample size, sample space. So the spade, there are 13 spade over 52, it is 1/4. Okay, now let's see what is the probability of B given A. So that's mean after you taking first card, what is the probability of the next card is a spade. Okay, so after you taking first card, since you are not replacing it, so you should have 51 sample size, and out of this 51 we have only 12 because you already picked one spade. Okay, so that's why you have to take one from the numerator and one from the denominator, because you already pick one spade. So this is already happened. So now we are going to find the probability of getting second spade. So that is 12 over 51. Okay, so the answer, the question asking here, first one is spade and second one is also spade. Okay, so the question asks to find the intersection. Okay, so that's another important part of this this class. So in this question, okay, both are spade means you have to find the intersection of these two defined events, A intersection B. And we can find the probability of A using the value here. And we can find the probability of B given A. So that's mean we are assuming, okay, A is already happened. What is the probability of happening B? So that's mean we already pick spade card. So there are 12 remains, and the total number of card also 52 minus 1. So we can find those values. Now use the idea of multiplication rule, which is PA times PB given A. Okay. So here, can you see when I'm writing B given A, this one should be matched with here. Okay. Okay, so now we can plug PA, which is 1/4 times 12 over 51, and this will be 0.0588. And when you are writing a decimal answer for this class, you should show at least, so you should show 4 decimal places. Okay, so if it is round, so if you are going to round, please round to 4 decimal places. Okay, so that's the important part. In your exams, homeworks, please round your final answer into 4 decimal places, final answer. Okay, so and in this question, it is important to figure it out, this one here. When you are writing PA first, so here should be PB given A. So here I write PA first because the given one here is A. Okay, and that's why I calculate PA as well, probability of A as well. Okay. Okay, so hopefully this makes sense. And if you have any questions, please feel free to ask questions. So I'm holding my next office hours on this Thursday from 9 to 12 p.m. Please feel free to visit me during that time, or send me an email, or you can provide your question into the discussion page as well. Okay. Okay, so now we are going to discuss the last example for this class, which is pairwise independent and mutually independent concept. Okay, so let's say so we have birthdays, and let's see Elias and Betty have the same birthdays. Okay, and Betty and Carol have the same birthday, and Carol and Alice have the same birthday. Okay, so before starting this question, I will assume this one for simplicity. Assume we have 365 days per year. Okay, so we are not going to consider leap years. Okay. Okay, so Alice and Betty have the same birthday. Okay, so event A says these two persons has the same birthday. So probability of that happen is 1 out of 365. Okay, and Betty and Carol have the same birthday. So Betty and Carol also have the same birthday. So the probability of happening, if you did not consider A or B, so the Betty and Carol have the same birthdays, 1/365, and similarly, the Carol and Alice has the same birthday, which is 1/365. Now we have 3 persons. Okay, so we have 3 persons. The question asks A and B are ABC are pairwise independent. So that means we have to check whether these two are pairwise independent, these two are pairwise independent, and B and C are pairwise independent or not. So we have to consider all 3 pairs. Okay. Okay, so now before starting to consider that one, I'm going to write this one. So we have Alice, Betty, and Carl. So we have only 3 persons. Okay. So, and if you want to write down the sample space, it will be something like this. Okay, so this is January 1st, has Alice's birthday, Betty has January 1st, Carol has the birthday in January 1st, and then 1, 1, 2. So that's mean Alice and Betty has the birthday on January 1st, and Carol has the birthday on 2nd. Okay, so 1, 1, 3. So these are the all possible cases. So if you can write, this will be this implies the sample size will be 365 to the power 3, because each item will go from 1 to 365. So the sample space will be 365. Okay. Okay, so I will show you how we can calculate this one. Okay. So the probability of A means number of different ways get Alice and Betty birthdays divided by total number of possibilities. So here, so the total number of possibility of getting Alice and Betty's birthday is 365 square, because we can pair these two, and this means we will have only 365 for event A. So event A, we have 365 to the power 2 number of items, pairs, and so that's mean if we write only for A, we can write the event like this. So 1 and 1. So this one means Alice and Betty has the same birthday, and Carol has the birthday on 1st as well. And 1 and 2. So the first one means Alice and Betty has January 1st, their birthdays, and Carol has the birthday on January 2nd. And likewise, we can write this pair. So it will be in A will be 365 square. Okay. So that's mean here in A 365 square, and in total number of possibilities 365 to the power 3. So it will be 365. Okay. So that means similarly we can find probability of B, probability of C, both are 1/365. So that's how you can find these numbers. Okay. Okay. Okay, so now we need to find A intersection B to show that this is pairwise independent or not. So let's find out. So I'm going to use this space A intersection B. So see the different here. Okay, so if you take the A intersection B, that means Alias, Betty, Carl, all three have the same birth. Okay, so A intersection B is same as. Okay, I will write here first. So if you take A intersection B, this is same as all three have the same birthday. So this is all three have the same birthday. So that means probability of A intersection B is going to be number of ways that all three have the same birthday. So that means you have 365 items. Okay, all three have the same birthday. All three have same birthday divided by all possibilities, all total possibilities. And you can show this one is 365, which is all three have the same birthday. We have 365 possibilities over 365 square, which is 1 over 365 square. Okay. So here 365 to the power 3. So those are the whole number of possibilities, the sample space, size of the sample space. And we can see this is same as PA times PB. So PA is 1 over 365. PB is also 1 over 365. So if you multiply this one, you will get this one. So this means A and B are independent. Oops. Okay, so similarly, we can say A and C independent and B and C also independent. Okay, so similarly, because we have to do the similar calculation, A and C, B and C also independent. This implies A, B, C are pairwise independent. So that's the answer for first part of the question. And now it is asking A, B, C are mutually independent. Okay, so if you have any question up to this point, please ask. And the next part, the question asks to find is this a mutually independent. Okay, so if it is mutually independent, we have to show this results. Okay, so we have to show, we must show this one. A intersection B intersection C is same as PA times PB times PC. Okay, so we have to show, we have to check this one. Okay, so in only for this case, okay, only for this according to this definition of ABC, so we can say, so A intersection B intersection C means, so we don't want to worry about PA, PB, PC because we have already find that one. We have to find this probability. Okay, so A intersection B intersection C is same, is meaning of all three have the same birthday. So this is same as A intersection B. Also, this is not always true, okay? Not always, not true in general, okay? So this is not true in general, only for according to the definition of ABC, this is true, okay? But not in general. Okay, so that's mean probability of A intersection B intersection C is same as probability of A intersection B, which is 1/365 square. Okay, so this is true only for this scenario, but not this is true for all cases. Okay. Okay, so now we have find this probability. Now we can check the product in the right hand side. So probability of A times probability of B times probability of C is same as 1/365 times 1/365 times 1/365, which is 1/365 square. Yeah, sorry, cube. This is cube. You are multiplying this one 3 times, which is not equals to probability of A intersection B intersection C. Okay. So because you have only 1/365 square in probability of A and B, A intersection B intersection C. So this implies A, B, and C are not mutually independent. Okay, so if you take A and ABC pairwise, it is pairwise independent, but if you consider all three at once, so then it is not going to be independent. Okay. Okay, so that's the end of this topic. And in the next class, I will start a random variable